Hello everyone, this is Yojana Fegade. Today we are diving into fascinating topic of artificial intelligence, that is state space search. Now you might be wondering what exactly is state space search and why it is crucial for AI. Well, buckle up because we are about to explore the exciting world of problem solving and decision making in artificial intelligence. So, what is state space search? A state space search consists of tree of symbolic stack that are generated when all possible operations are iteratively applied to the current state of symbol. At its core, state space search is like a GPS for artificial intelligence. Imagine you have a complex problem to solve and you need to navigate through all possible scenarios to find the best solution. That's where state space search comes in. Now, just we can just break down the state space search. Okay, so we can now deep dive into state space search. The state space search is divided into three states, that is the initial state, intermediate state, and the final state. Every journey begins somewhere. So, in state space search, we start what we call at the initial state. This is our starting point, the current configuration of the system we are dealing with. So, basically, initial state is a start where we can start solving the problem. The second state is intermediate state. Intermediate state is a solution to the problem in a sequence of operations that maps the initial state to the final state. That is, the in between states that are generated are called intermediate states. Now let's move on to the final state. So we need to know when we have reached our destination. The goal test helps us to identify if a particular state is our solution or not. Additionally, there's the path cost, the price we pay to get from one state to another state. So basically, final state is the final solution of our problem. As we can see in the slide, this is one of the representation of the available states in our state space tree. The first one is the initial state. The goal state can be any of these, and these are the intermediate states that are generated. Now our next topic is transition model. So as we take actions, we transition from one state to another state. The transition model describes how our actions change the current state. It's like a set of rules guiding our journey. As we can see here, the state of vacuum cleaner is changing in every state that is produced. So the model describing the state change is called as transition model. So, by the algorithms we have learned till now, with this component, state space search becomes a powerful tool for solving complex problems. Now, let's explore how we navigate through this space using different algorithms. Algorithms for state space search. Alright, let's talk about our first algorithm, that is breadth first search algorithm or BFS. Imagine you are exploring a tree like structure, and with BFS, you are like a diligent explorer checking each level before moving to the next. This ensures that you don't miss any possibilities at a given depth. So, in short, BFS explores all nodes at the current depth before moving on the next depth. Now, let's switch gears to depth first search or DFS. Imagine you are more of an adventurous risk taker. With DFS, you plunge into one branch, explore as far as you can, and backtrack only when necessary. It's sort of bit daring. In short, DFS explores as far as possible along each branch before backtracking, and if necessary, then only it backtracks. Lastly, let's talk about A-star algorithm. Think of it as the best of both worlds. It combines the systematic approach of BFS with a touch of optimality. How? Through heuristic function that guides the search. Our heuristic function helps us estimate the cost to reach the goal, allowing A-star to prioritize more promising paths. It's like having a GPS that not only knows where you are but also suggests the most efficient routes that are available. So our A-star is efficient because it combines breadth first search as well as the optimality using heuristic function. Now let's focus to the interesting area, that is the application. One classic example is puzzle solving. Imagine you have 8 puzzle and you want to rearrange the tiles to reach the goal state. State space search helps us to find the optimal sequence of moves. In the 8 puzzle problem, the number of misplaced tiles is considered as our heuristic function. Next up, let's talk about robotics. Picture a robot in a maze. Try to imagine that. So, in state space search, it helps us it helps the robot to find the path efficiently, avoiding obstacles and reaching the destination. Lastly, let's consider game playing. Whether it's chess or any other strategy game, state space search allows game playing agents to evaluate different moves and choose the one that leads to victory. Now, as powerful as state space search is, it comes with its own challenges. One major challenge is exponential growth. The number of possible states can explode, especially in larger problem domains. Here we can see how the growth is increasing at an rate. Imagine that you are playing a game on a massive board. In that, the state space can become overwhelmingly vast, making it challenging to explore every option and find a goal state. Another consideration is the balance between heuristic and optimality. Heuristic provides shortcuts by estimating the cost to reach the goal, but there is a trade off. Let me explain. We know that accurate heuristic can speed up the search, but sometimes overly optimistic heuristic can might sacrifice optimality. It's delicate balancing act that varies depending upon our problem. So these are the two challenges that we face in state space search. So this was all about a state space search, its challenges, then algorithms and all. I hope that you got something through this video, and thank you very much.